Hello, and welcome to the third and final module in the Life Cycle Assessment in Practice series. Today we'll cover whole building life cycle assessments with a special case study project. My name is Pete Choquette, Principal and Director of Design at Epstein Group in Atlanta, Georgia. I'm joined today by Dr. Liz Monet, our life cycle assessment expert, who's responsible for all of our environmental product declaration and whole building life cycle assessment projects. At the end of today's course, participants will be able to recognize the software packages available for whole building lifecycle assessments and how BIM can be utilized to streamline lifecycle assessment analysis. They'll also understand the type of data and quantity takeoffs necessary to complete a whole building lifecycle assessment, how manufacturers' data informs a whole building lifecycle assessment, and finally, how to interpret the results of a whole building lifecycle assessment and the environmental implications of different material selections. Before we begin, though, it would be good to start with a brief refresher about whole building life cycle assessment. A whole building environmental life cycle assessment measures the environmental impacts of materials and building projects in a number of areas, including embodied energy, which includes how much energy was involved in making the material, global warming potential, how much CO2 was produced in that process, tropospheric ozone, which speaks to ground level contributions to smog, stratospheric ozone, which speaks to the potential to damage the ozone layer that protects us from UV radiation, eutrophication, which occurs when fertilizers and other organic materials upset the balance of ecosystems by catalyzing algae blooms or red tide, and acidification, which creates phenomena like acid rain. Whole building life cycle assessment utilizes a cradle-to-grave system boundary, which encompasses all environmental impacts from material extraction to a building's end of life. So if we look at the system boundary for whole building life cycle assessment, it includes not only the extraction and manufacturing of building materials, as is typically included in a cradle-to-gate analysis, but it also includes the environmental impacts of transportation to the site, construction, operation and maintenance, and end-of-life environmental impacts as well. Note that a cradle-to-grave analysis does not easily capture additional impacts and benefits from reuse, recycling, or repurposing of building materials after their first pass through the life cycle. These impacts are difficult to quantify given the uncertainty of the number of life cycles a material may go through and all the potential uses it may have. Aluminum could, theoretically, start life as structural framing, then become a window frame in its next life, and later still become a soda can. Clearly defining a realistic system boundary then becomes difficult in that cradle-to-cradle scenario. A whole building life cycle assessment can be used to assess the environmental impacts of a building project, providing the design team a tool for improving the environmental performance of a project during design. And it can also be used to document potential lead credits for whole building life cycle assessment. Whole building life cycle assessment can be found in the LEED rating system in two forms. In LEED version 2009, it had existed as a LEED Innovation and Design Pilot Credit, Materials and Resources Pilot Credit 63, Whole Building Life Cycle Assessment. In LEED version 4, whole building life cycle assessment is an optional compliance path for materials and resources credit, life cycle impact reduction. In LEED version 2009, the requirements for materials and resources pilot credit 63 were as follows. Project teams had to demonstrate a minimum of a 10% reduction in environmental impacts in 3 of 6 categories relative to a baseline building. The 6 categories were the ones we've already touched on: primary energy, global warming potential, tropospheric ozone, stratospheric ozone, eutrophication, and acidification. In addition to showing improvement in 3 of 6 categories, no other category could be worse than the baseline building in environmental performance. And finally, the baseline building had to be a building of similar geometry and use as the design case building, with a minimum service life of 60 years, utilizing the same operational energy consumption that was calculated in the LEED energy model. In LEED version 4, which was patterned after LEED Pilot Credit 63, whole building life cycle assessment is one of 4 potential compliance paths for achieving materials and resources credit life cycle impact reduction. The first 2 compliance paths, each worth 5 points, reward project teams for renovating historic buildings or abandoned or blighted buildings. The third compliance path, which is similar to the old LEED version 2009 credit for building reuse, rewards project teams for reusing prescribed thresholds of the existing building envelope structure or interior elements for 2 to 4 points. And finally, project teams may achieve a whole building life cycle assessment credit to earn 3 points. Note that this gives project teams an opportunity to earn points in this credit even if they are doing a new ground-up building, which was not a possibility in the old LEED version 2009 building reuse credits. Similar to LEED version 2009 Materials and Resources Pilot Credit 63, the LEED version 4 credit requires project teams to use a whole building life cycle assessment to demonstrate at least a 10% reduction in environmental impacts in 3 of 6 categories. However, one of those categories must be global warming potential. Additionally, no other category may show an increase of greater than 5% in environmental impacts, which is a little less strict than the old Materials and Resources Pilot Credit 63. As with that pilot credit, the baseline building has to be of a similar geometry and use, with a lifespan of at least 60 years, and energy consumption matching what is calculated in the LEED energy model. Note that the materiality of the baseline building is required to match the prescribed materiality of the building as defined by ASHRAE 90.1 Appendix G, which, as you'll see, is advantageous to some building types and less so to others. So now let's see how a whole building life cycle assessment applies to a real-world project. For that, we've selected an architectural project that we're currently working on in our office for Zoo Atlanta, the renovation of the Grant Park Cyclorama building. To give a brief overview of the history of the building, it was originally constructed in 1921 to house the Cyclorama painting The Battle of Atlanta, which is a giant painting in the round measuring approximately 50 feet high and 400 feet long. At the time of its creation, it was the largest oil painting in the world, which is a distinction it still claims, although there's a little dispute with the keepers of the Gettysburg Cyclorama painting. The painting was originally commissioned in 1883 by Illinois Senator John A. Logan, who was an officer in the Union Army in the battle and had designs on running for president. Unfortunately, Logan died in 1887 before the painting was completed, leaving the German artists who worked on the painting out of their studio in Milwaukee, Wisconsin, to unsuccessfully attempt to recuperate their money by touring the country with the painting. Eventually, they sold it in 1888, and after changing hands several times, it came into the possession of Atlanta businessman George Gress in 1893. Gress donated the painting to the city of Atlanta, where it was displayed in a wooden building in Grant Park until 1921, when the current building was built to alleviate fears about displaying a highly flammable oil painting in an equally flammable wood frame structure. In 1981, a major renovation of the building was completed that included removing the central column in the cyclorama and replacing it with an exterior space frame truss that created a free span inside the building to allow for the installation of turntable theater seating for viewing of the painting. Both the cyclorama painting and one of the building's exhibits, the locomotive the Texas, were listed on the National Register of Historic Places, and the cyclorama building itself is a contributing structure to the historic Grant Park neighborhood, which is also on the register. However, in 2014, it was announced that due to low attendance and rising maintenance costs for the existing building, the painting and exhibits would be moved to the Atlanta History Center in the Buckhead area of Atlanta. So the city turned to Zoo Atlanta, which sits adjacent to the Cyclorama building, to see what new use could be envisioned for the facility. And as a part of taking possession of the building, the zoo asked for 3 acres of land to the east of the building with a bold vision of completely reshaping the zoo. The 3 acres will be used for an expanded African savanna exhibit to include giraffe, hoofstock, and a new African elephant exhibit and holding barn. The savanna will be visible from a new event space inside the Cyclorama, which inhabits 2 floors over the zoo's relocated administrative offices. By relocating the administrative offices to the Cyclorama, the zoo's old administration building, which currently blocks the existing zoo entrance from the main Cherokee Avenue surface lot, can be removed and replaced with a brand new entry plaza to help enhance visitor experience and improve zoo operations. Because the project is being constructed on land leased from the City of Atlanta, both the Cyclorama building and the elephant barn are required to achieve not less than LEED Silver certification. As a part of the project's LEED effort, the design team has committed to performing a whole building life cycle assessment on the Cyclorama building in an effort to try to quantify the environmental impacts avoided by renovating a historic existing building. So why should we renovate historic existing buildings? The most obvious argument is that these buildings are important cultural resources that need to be retained. As William Murtaugh, the first keeper of the National Register of Historic Places, once said, "It has been said that at its best, preservation engages the past in a conversation with the present over a mutual concern for the future." Most designers understand this concept, but now we're also learning how important existing buildings are as both an environmental and a socioeconomic resource as well. In 2011, the National Historic Trust for Preservation released the study The Greenest Building, quantifying the environmental value of building reuse. Utilizing whole building life cycle assessment techniques, the study showed the renovation of a mixed-use building in the Atlanta market, for instance, reduced environmental impacts by as much as 20% relative to a new building, even when that new building was 30% more energy efficient than an average building. Likewise, existing buildings play a key role in the socioeconomic landscape of our cities as well. Famed urban theorist Jane Jacobs claimed in her book, The Life and Death of Great American Cities, that in order to have a thriving urban district, buildings must be mingled in their age, condition, and required economic yield. In 2014, the National Trust for Historic Preservation and Green Lab published Older, Smaller, Better, measuring how the character of buildings and blocks influences urban vitality. Proving Jacobs' point, the study showed neighborhoods in Seattle with greater mixes of renovated existing buildings had nearly 36.8% more jobs per square foot and nearly double the woman and minority-owned business participation. Similar neighborhoods in San Francisco had 30% more jobs from small businesses as well. Intuitively, it's easy to understand why. Very few small businesses can afford Class A office space in downtown glass and steel office towers. Therefore, renovated buildings near urban cores can act as important incubators for small businesses, which in turn helps spur job creation and innovation in the local economy.
Hello everyone, this is Liz Monet, and I am going to pick up on where to begin the whole building LCA. So again, the first question here is, should you do it in-house or have it contracted? First question would be, does your company currently have the capacity to do its own whole building LCA? This involves having the software and an employee trained in LCA. Also, do you have the BIM files for the building and a baseline comparison building? If you don't have either, you may need to look for a consultant in whole building LCA. However, as you will see, the LCA building software is a little more intuitive than the LCA practitioner tools needed for the product LCAs. Therefore, it may be possible to do a whole building LCA with either the BIM files or a motivated employee who would like to learn the software. Okay, next we'll look at some of the popular building LCA softwares. Here we can see there are kind of two sections. There's the design team LCA tools, which are made to be usable by architects, engineers, and anyone with an interest. And we'll also see that you can use the LCA practitioner tools we talked about earlier as were used in the product LCAs. And those are Gabby and SEMA Pro. For the design team LCA tools, we can see Athena Impact Estimator for buildings, LCA Design, Invest2, and Tally. There are also more out there, but these are some of the popular ones. When you look into the guidelines for the whole building LCA, however, you will note that the Athena Impact Estimator for buildings, Gabby, and SEMA Pro are the only approved softwares by LEED to conduct the whole building LCA. Next, we'll look at the steps to complete the LCA. Note that these will vary somewhat by software, and for today, we will be focusing on the free and widely used Athena Impact Estimator software. The LEED guidelines for building LCAs do define the scope, and the scope is required to be cradle to grave for building LCAs. So here we will see included raw materials, manufacturing, construction and installation, use and maintenance, and demolition and end of life. Let's also take a moment to note some of the guidelines for modeling buildings for the LEED credit. The requirements here are that, again, it's cradle to grave, a 60-year service life for the building, and that this is compared to a baseline building. Now, both of these buildings have to meet the ASHRAE requirements, and the baseline building has to have the same gross square footage, orientation, location, and function as the proposed building. By function, we mean, say, a retail space has to be compared to another retail space, or a laboratory must be compared to another laboratory. Additionally, the baseline and proposed building need to meet EA prerequisite minimum energy performance requirements. Operating energy is generally a very significant piece of an LCA. So the LEED guidelines require that both buildings meet the EA minimum energy performance requirement, as well as have the same operational use so that the results are not skewed by operational energy. The actual model of the building, or what is input into Athena, will include the building envelope and structural elements. Now that we have discussed the scope and LEED requirements, let's move on to the case study that Pete discussed, the Cyclorama renovation for the Atlanta Zoo. If you decided to download the Athena Impact Estimator program in order to follow along with us, go ahead and open that up now. Okay, here's the first screen you will see when you open up Athena. You will see the impact estimator for buildings on the left, and right now there are no projects open because we haven't started one, so let's go ahead and look at how to start a project. Alright, so if we go ahead and click File and New, we will see a window pop up to add a project. Let's zoom in a little closer so you can see what's happening here. Okay, so I'm going to go ahead and name my project Zoo/Cyclorama Renovation. And next, I will choose the city which is closest to me, or the city with the closest climate. In this case, we are in Atlanta, so easily enough, we will pick Atlanta as our location. However, Athena only has 8 US locations and then 1 general USA project location. So you may need to choose a different city than where you actually live. You'll want to choose the city with the climate closest to the city you are in, which may be the city that is closest to you. Next, we'll see that we have 8 possible building type options to choose from. These include options like commercial, institutional, industrial, or single-family residential. For this project, we're going to go ahead and select commercial. Next, we'll see that we can select the building life expectancy. Now, this is required by LEED to remain at 60 years, so we'll just go ahead and leave that as it is. Then we can go ahead and decide if we want SI units or imperial units. Because this is a US project and we're used to seeing feet and square feet, we'll go ahead and select imperial. That's what most of our units are in that come from the Revit model and other models. Once we have selected imperial units, we will see that we are offered building height and gross floor area in feet and square feet. I've already gone ahead and entered the numbers for our project here. Another item I'd like to note, which is down at the bottom of this pop-up, is the operating energy consumption. For our particular project, we have not completed the energy modeling stage yet, but if you click this window, you will see options to enter the operating electricity, natural gas, etc. for the building. Because we don't currently have that information, and because the operating energy performance needs to be around the same for both the proposed and the baseline building, we're going to go ahead and skip that for today. We'll go ahead and hit OK here and then move on to the next screen. Okay, so now back at our home screen, we see on the left-hand side under the impact estimator for buildings that there is a project. If we go ahead and double click, you can edit those inputs that you entered for the project at any time. Also, you can go ahead and right click, and then we will see that a number of options appear. We're going to go ahead and go through the process of adding an assembly. So let's start off by adding a roof assembly, and for this building we are looking at an open web steel joist. Once you have selected an assembly, a pop-up will show up like this one that allows you to enter in the information for that assembly. For this project, we have 2 types of roofs. The first one we are going to enter is the roof with TPO coverings. Now, the Cyclorama building is a very creative, different shape than you'll normally see in a building, but that is not something that Athena will let us enter. Instead, we are looking to get the roof area to be about equivalent to what the total roof area is of the Cyclorama building. From there, it will analyze the amount of materials needed, and that's about as close as we can get. So we know that our roof area of the Cyclorama, that is TPO roof, is about 18,255 square feet. So I played around here with the width and the span of the roof to get the closest possible answer to that. This, of course, will not be a fully accurate answer, but it should get us in the ballpark of the amount of materials needed. The other defaults here look correct, so we will just leave those and move on to the envelope tab. Once we get to the envelope tab, we can insert different materials. So if we look through the drop-down menu of assembly groups, we can choose roof. And in the envelope category, we can choose the roof envelopes. From here, like I said, this is a TPO roof. So we're going to go ahead and add a TPO membrane. There are plenty of other materials to add here, such as insulation, asphalt, shingles, etc. I won't go through all of the details of the roofing assembly needed for our building, but I did want to show you how these different inputs are added into Athena. So we went ahead and added everything we needed to for our roofs, and when we pull up our home screen, we can see on the left-hand side that we have added our two different types of roofs. Now we want to quickly look at the other way of inputting materials into Athena Impact Estimator. Now you can enter all of the assemblies the way we did, or you can go ahead and do a bill of materials file import. If you have modeled your buildings in a BIM software, this may be the easiest way to conduct the LCA. However, of course, your information is only as good as your model. Okay, so once we've right-clicked our project again and hit BOM file import or bill of materials file import, we'll see a new pop-up window. For our project, we used the Revit model and took the bill of materials from there. We created a file in Excel that included all of these materials. Once we narrowed down the materials related to the structure and the envelope, we finalized that Excel file, and here we are going to import it into Athena Impact Estimator. So first thing first, we'll go ahead and hit Browse and look for that file. Once we have found that file, the Athena Impact Estimator automatically recognizes that it's an Excel file and shows us this menu. The pull-down menu includes all of the different sheets that are included in that Excel file. So we have all of the things related to the proposed building and the existing building. The sheet we're going to look at right now is related to the new building or the proposed building, and we'll look at the materials that are sorted by square footage. Now you can have everything in the same Excel file, that's fine, or you can look at them separately. In this case, it was just easier for us to sort by the units of measure. Once we have selected our sheet, we'll go ahead and hit the load button. And once we've loaded, we will see a whole bunch of data that is from that sheet has come up into Athena. Our step 1 status at the top of the bar is now green, meaning we can move on to the next step. But before we do that, I would also like to note the green check marks that are over on the left-hand side. We'll see these are flagged as lines that are not data, so they will be skipped when the file is analyzed. Okay, so step 2, we're going to map the columns. Here we will see that Athena already recognized that column 3 is our unit of measure column, and that column 2 is our quantity column. However, it did not recognize column 4 is our material name column. So we'll go ahead and go to column 4 and do the pull down menu here and click material name. Once all 3 of these columns are mapped, the quantity, unit of measure, and material name, the step 2 will turn green, and we will go ahead and hit step 3, map the rows. Now for step 3, we're actually trying to map the data that we have to the data that is in the Athena Impact Estimator database. So for example, here we have gypsum, and we're going to look for that in the database by going to the pull down menu for material type and gypsum. And then we're going to see a variety of different gypsum types. In our case, we were looking for 5/8 of an inch regular gypsum board, so we'll go ahead and select that, and that will map all of those gypsum products. All the materials that are named the same thing, gypsum 5/8 of an inch, we'll see those autofill and green check marks beside all of those products. Okay, so we went ahead and mapped all of those columns based on the information that we had. And once we have finalized those steps, all of the top steps will turn green, and we can go ahead and hit OK. Okay, so we went ahead and did all of the products for both the renovation, which is the proposed building, and the existing Cyclorama building, or the baseline building. On the left-hand side of our screen, you'll see that there are 2 different project files here. Once we have entered all of this information, we can go ahead and compare the 2 buildings. We'll go ahead and look at the reports, and once we hit reports, we will see a new pop-up menu. Now on this pop-up menu, we'll see 3 tabs: project reports, project comparison graphs, and rating system reports. Now, considering what we've been talking about today is LEED, rating system reports sounds like a good place to start, so let's see what's there. When we click on over to rating system reports, we can immediately see that LEED is actually one of the rating systems that is a part of the Athena Impact Estimator database. So by choosing this report, you will actually get the information that you need to report in LEED. So for our project, we'll go ahead and set the reference design as the existing Cyclorama and the proposed design as the Zoo Cyclorama renovation project. And we're going to click LEED and then A through D. Now A through D or A through C, those are both related to the scope of the project. We will see later that A1 to A3 is related to the product life cycle stage. A4 through A5 is related to the construction process. B2 and B4 is related to the use phase. B6 is related to the total operational energy. And C1 through C4 is the end of life. And then D is beyond building life. For your LEED project submission, you only need to include A through C because that will get you through the end of life. But just for show, we'll go ahead and look at D to see if it has any significant impacts on our results. Once we have made those selections, we'll go ahead and hit Show Reports. Okay, so this LEED project comparison report is generated to compare our 2 projects, the reference design building and the proposed design building. And now these are some interesting results. What we see is a very significant difference in pretty much all of the different impact categories for LEED. Now at this point, I would like to note again the importance of your bill of materials coming from your Revit model. Again, your bill of materials is only as good as what is entered into the Revit model. So here we can see that maybe there could be some issues. It looks maybe too significant. So that's something that we're going to want to look into. Just by looking at these numbers, it is my strong suspicion that we could be missing some materials within the proposed design model. And that is likely due to the fact that this is a renovation project and all of the materials from the previous building may not be entered into the proposed model. Again, we need to make sure that the simulation includes all of the structural and envelope materials for both designs. For the purposes of this course, we'll just note that this is a working model, but we can still look at the results as you would look at yours when you do such a model. For the time being, let's just go ahead and assume these results are correct. And we will address how we can look into those issues later. So if these were correct, we get a big check mark on LEED because our percent improvement for the proposed design is much greater than what is required by LEED for either the V2009 or the V4 requirements. Okay, so now let's look at some other ways to compare the two designs that we looked at. We'll go back to that pop-up screen for reports and look at the project comparison graphs. Here we can select both of the projects because we're going to compare them again, and then we'll select all of the summary measures that are included in the LEED requirements. Quickly, we'll run through some of those reports and see if we find anything interesting. Okay, so first we'll look at the non-renewable energy, and it's sorted by life cycle stage. First, I'd like to note that in many of these reports, you'll see that the total operational energy can be a very dominant force in the life cycle stage assessment. However, as we noted earlier, we have not run the energy models and we have not entered the total operational energy. Therefore, on these graphs, we are just going to see 0 megajoules shown. So what we do see, since we have excluded the operational energy, is that the product life cycle stage is very dominant in the assessment of environmental impacts for non-renewable energy. The other stages, including the construction process, use, and end of life, are relatively small in comparison. That tells us that our products are using a significant amount of non-renewable energy, and that could be a place that we could look for environmental performance improvements. As we flip through the other results, we can see similar things for acidification potential. Again, we see this with the global warming potential. Another thing I'd like to point out on this global warming potential slide is that we see again that quote-unquote negative impact that we saw in the product life cycle assessments. So here in the beyond building life, we see that the zoo Cyclorama renovation uses a material or product that actually decreases the CO2 equivalent effect of the building. Now, negative impacts can come, like we saw in the other module, from things that absorb CO2 or could potentially be reused in a later project, for example. Okay, moving on to ozone depletion, we again see similar results where the product is the dominant phase, although we do see that the use phase is a little more significant here, with the renovation actually being higher than the existing cyclorama. From that, we can surmise that the renovation project has something that requires more maintenance or perhaps more replacements than the existing project. However, we're only looking at that as it relates to ozone depletion potential. Now, when we look at smog potential, we will see that the different life cycle stages are much more closely aligned. We can see that the product, again, still dominates the life cycle stage assessment for smog potential. However, construction processes are a big impact here as well, and we'll see end of life as another significant impact. Lastly, we can look at eutrophication potential, and again, we'll see that the product is the most dominant life cycle stage. But some of the other stages are fairly significant here as well. So as we've looked through all of these different environmental impacts, we can tell that our products are really driving a lot of these environmental impacts. So what about the products is doing that? We can go ahead and go back over to the reports pop-up window. And when we go to the project reports, now we're only looking at one report at a time, or one project at a time. We can look at a graph that shows the assembly group embodied effects. The embodied effects of an assembly group can help us better target what could be occurring in terms of, say, are the beams a significant contributor, or is the roof a significant contributor? So we'll go ahead and look at that here. Now, it's at this point that we'll note another folly of doing the Athena impact estimator in terms of BOM, or bill of materials input, because when you do that, everything is input as extra basic materials. So when we look at the assembly groups, all we can really see here, what we modeled, are the extra basic materials, which is everything else beyond the roof, and then the roof assembly. Athena doesn't know how to sort your bill of materials into, say, beams and columns or foundations, so that's why we're only seeing the extra basic materials for the bill of materials input. Now, if you're doing your modeling differently and you enter in all of your materials via the assembly option, you go through and you enter your concrete columns along with your steel roofing, say, and your walls made of gypsum. They will be sorted into categories, and that will give you a better idea of how the different materials could be impacting your results. So this particular graph, we looked at global warming potential, and we can see that the extra basic materials, or basically all of the other materials beyond the roof, are contributing quite a bit to the overall impact, but the roof is also a significant impact driver. So again, it's hard to tell in our particular simulation what materials are driving what. So another way to look at this is you can go through and compare materials in a test where you just have the same exact building and then you change one material and see how that affects your overall results. And this is really what LEED is trying to get at and what Athena is trying to get at is to help you design a better building by choosing materials that are better than other potential materials you could choose. So if you model a double pane window versus a triple pane window, you can see how that affects your overall environmental impact. Now, I'd like to suggest that if you are using Athena as your modeling software for the building LCA credit, there are a number of great tutorials to using Athena on YouTube, so go ahead and log in there. You will get a much more detailed tutorial than we can cover in this course, but it is a useful tool. You can use this tool towards the LEED credit, or you can work with LCA practitioners using the Gabby tool or the SEMA Pro tool. Now, there are occasions when that may be preferred. As you can note, the database is a set number of items within Athena. So if you are using a number of materials that are different and more sustainable in a way that Athena cannot capture, it might be worth doing a different type of environmental assessment. Okay, now as a quick overview of what we've learned from our assessment of our two different designs in Athena, it's pretty clear that perhaps all of the materials have not been input into the Revit model. So we will have to either revisit the Revit model, or we will need to add the assemblies one by one into Athena. But we can note that renovating a building, because it's keeping the majority of the shell structure, does result in a significant environmental reduction. So if you think about it as the number of materials that we are adding, because we are reusing a number of materials, that would be a correct assessment of how much we are reducing. However, LEED requirements require you to model all of the different structural and envelope materials, and I think that we can say here that our Revit model is missing some of those materials. As we discussed, you can also use the results to identify the life stages and materials which cause the highest environmental impacts. So if you enter all of that via assemblies, you can go through and say, oh, our concrete columns are really causing the most significant impact. Perhaps we can try a different design. And that leads us to another thing we can use the results for, and that's in the design phase. We can try a number of different alternate materials and products and see how that impacts our overall environmental performance in order to optimize the design. So hopefully now you have a good idea of what a whole building LCA is and how it is conducted. So let's go ahead and review what we have learned today. Today we covered the LEED credits that are related to whole building LCAs and how you can go about achieving them. And we also talked about the process to conduct a whole building LCA. And lastly, how to interpret the results. Let's cover a couple quick questions to review what we've learned in the module today. Okay, true or false? You can attempt the building LCA credit in LEED version 4 or LEED version 2009. And the answer is true. If your project is LEED V2009, then you can attempt this credit as the pilot credit 63. Or if your project is a LEED V4 project, you can use the material and resource credit in V4. How many impact categories can increase in the pilot credit for version 2009? And the answer to that is actually 0. That requirement has actually changed in the new version of the credit for V4. Okay, so LEED V4 does allow an increase in some impact categories. So my question is, how much can the impact categories increase? And the answer to that is 5%. For the V4 credit, 3 categories must decrease by 10%. However, the other 3 categories are allowed to increase by up to 5%. The baseline building when comparing building LCAs does not need to have the same blank as the proposed building. And the answer we're looking for here is envelope assemblies. When applying for the LEED credit, the other elements here need to remain the same. So orientation, gross square footage, and operating energy performance. Additionally, the service life and the function of the building need to remain the same. What are some of the limiting factors of using a tool like Athena Impact Estimator instead of a tool like CIMAPRO? Of the answers here, we were looking for the fact that A, it has a relatively small and set database of materials. Also C, the ability to choose a weighting method for an overall environmental performance score. This is done often in product LCAs, but in the case of building LCAs, what we're looking for in terms of output are those 6 impact categories to compare. Our last question has to do with analysis of the impacts. If 2 buildings are modeled in compliance with the LEED guidelines, but one has substantially larger effects than the other, where can we look for discrepancies? So the answer here is actually all of these places. We can look for answers within the bill of materials, seeing if the amount of materials for the building is correct and similar. We can also look at the life cycle stage graphs and tables to analyze if certain stages are particularly impactful for either building. And if we entered our categories in by assembly groups, we can also look at the assembly group embodied effects to see if there's a difference in, say, the steel joist or a wood joist that would be causing a dramatic effect on the overall impact. This concludes our final module. Thank you all for joining us. We hope you learned a lot from the course and were able to get some great takeaways on how to understand and participate in doing product LCAs and or whole building LCAs.